We've been basically conditioned to believe that building a smarter AI just means, well, building a bigger brain.
Right, the whole scaling laws narrative.
Exactly. Just pumping massive server farms full of more data, racking up the parameter count and assuming raw intelligence will just magically solve every bottleneck. But for you listening today, we're looking at something different. Because the actual secret to a truly self-improving agent might not be the brain at all. It's the tool belt.
It's a complete paradigm shift. We're finally moving away from evaluating an AI purely on its internal neural weights. And we're starting to look at how it actually engineers its own external environment.
Which is huge.
Yeah. I mean, if an agent can actively build, refine, and, repair the software it uses to interact with the world while explicitly documenting its past failures, the ceiling for autonomous capability just gets exponentially higher.
Right. And that brings us to our mission today. We are doing a deep dive into a state-of-the-art paper by Yangbo Wei and colleagues. It's called SkillSmith, Co-Evolving Skills and Tools for Self-Improving Agent Systems. So, okay, let's unpack this. To grasp the magnitude of this framework, we have to look at the architecture of modern AI agents.
Right, because they aren't just, predicting the next word in a chat window anymore.
Exactly. They rely on this external state that's maintained completely outside the core model. You essentially have these two distinct layers. You've got skills, which operate as the orchestration logic, like the instruction manuals or the workflows.
Like how to research a topic.
Right. And then you have tools, which are the actual executable code, the Python scripts and APIs making the physical calls.
And the fundamental flaw in almost every current self-improving framework out there is that they only allow the AI to iterate on that first layer.
The instruction layer.
Exactly. The orchestration logic can evolve, it can get smarter, but the executable code layer, the tools, are entirely frozen. The AI is literally locked out of its own tools.
So it's basically the equivalent of handing a master carpenter a broken hammer with like a loose handle and a chipped head and telling them, they're strictly forbidden from repairing or replacing it.
Yeah, good luck building a house with that.
Right. That carpenter is forced to invent this ridiculously complex, awkward way to swing their arm just to drive a single nail. The energy they spend compensating for the bad tool completely overshadows the actual work. Is that essentially what's happening to the AI?
It's exactly what's happening. In the paper, the researchers actually document this phenomenon. They call it the proliferation of bloated or brittle skills.
Bloated skills, okay.
Yeah. So when a tool fails, say, I don't know, an API endpoint is slightly deprecated or a document scraper hits a weird formatting quirk, the system restricts the AI from modifying the underlying Python script. It can't fix the scraper.
So that the tools are frozen.
Right. So the agent's only recourse is to overcompensate at the skill layer. It starts generating these massively convoluted prompts. It adds ad hoc offsets, weird heuristic rules, highly specific conditional logic, just trying to force this broken tool to output something remotely usable.
Which means the AI is basically using prompt engineering as a Band-Aid for bad code.
Yeah.
I can't imagine that scales well when you deploy an agent in a complex environment.
Oh, it flatlines completely. It just hits a wall. The researchers tested this baseline approach on the Wildclaw benchmark, and that's a rigorous simulation of real-world agent deployments. We are talking about complex, multi-stage tasks that require, anywhere from 15 to 50 distinct steps to complete.
Wow, okay. It's a pretty heavy logic.
Exactly. And when agents are restricted to evolving only their skills, the skill library just inflates with all this redundant junk. The baseline model actually bloated up to 16 overlapping skills.
16?
Yes, 16 different skills trying to route around one single bad tool.
It's spinning its wheels. It's writing 16 different instruction manuals on how to hold the broken hammer, but it's still not fixing the hammer.
Exactly. And by day 2 or day 3 of the simulation, the performance curve goes entirely flat. The agents literally stop improving because you simply cannot write a good enough natural language instruction to bypass fundamentally broken underlying logic.
Right. So the obvious answer, if you can't prompt your way out of a broken API, is to let the AI rewrite the code. But wait, if we just give an LLM unconstrained access to rewrite its own underlying code base, that feels like a recipe for absolute disaster.
It's terrifying, honestly.
Yeah. I mean, won't it just hallucinate a library into oblivion or, accidentally delete a critical dependency?
That is the exact risk. And they tested that too. If you allow what the literature calls free tool evolution, which is just unconstrained free text code generation, the system's error rate spikes to 14.7%.
Oh, wow.
Yeah, that is nearly 5 times higher than the baseline. I mean, it might successfully patch one localized tool, sure, but it introduces these fatal syntax errors or logic bugs that cascade and break the rest of the system.
So the real challenge for SkillSmith is giving the AI the power to fix the hammer without it accidentally, mutating the hammer into a saw or just something completely useless.
Precisely. And SkillSmith solves this through its first major architectural innovation. It's called the Unified Proposal Space with Typed Operations.
Typed operation.
Right. The framework does not let the agent blindly rewrite code from scratch. Instead, it restricts the evolution of the tool belt to 5 highly specific, safe atomic operations. And those are wrap, edit, compose, split, and retire.
Okay, so the first 3, wrap, edit, and compose, those make intuitive sense for building out capabilities. But I'm curious about the destructive ones, or I guess subtractive operations. If a tool is just performing terribly, I assume the AI can't just delete it if other legacy workflows are still blindly calling that script.
Right. Exactly, and this is why the retire operation is so elegantly designed. It doesn't just nuke the file. When SkillSmith retires a tool, it explicitly maps out every single legacy skill that depends on it, and then it reroutes those dependencies to a newer, more efficient tool.
Oh, that's smart.
And Split functions similarly for overloaded tools. So say you have a massive monolithic script that both scripts web data and parses JSON.
Right, a dual-purpose tool.
Yeah, and let's say the parsing function keeps failing. This split operation safely divides up into 2 modular tools, so the AI can then patch the parser without risking the scraper.
Okay, but the genius of this structure really shines in how SkillSmith applies these operations. The paper calls it an atomic bundle.
Yes, the bundle is crucial.
Because, you wouldn't push a massive back-end database schema change without updating the front-end API calls at the exact same time. SkillSmith applies that logic to the AI's internal state. It updates the executable tool and the orchestration skills simultaneously.
And the Office QA case study in the paper is just a perfect illustration of why this atomic synchronization is necessary.
Right, let's look at that.
So the benchmark tasked the AI with a financial data extraction. The question was, what was the total change in federal debt held by the public between Q1 and Q3 of FY 2019?
A very standard yet highly specific corporate query. And the baseline AI basically bombed this completely, right?
Totally failed. And it comes down to a classic broken hammer. The tool the agent relied on to extract tables from PDF documents used a very rigid integer indexing method. It just literally counted rows and columns.
Like go to row 5, column 3, extract the value.
Exactly, which works perfectly on a pristine standardized spreadsheet. But the U.S. Treasury document contained a table with merged headers.
Which instantly breaks integer counting.
Instantly. The tool's rigid counting was thrown off by one single merged cell, so it blindly grabbed the wrong column, performed the calculation on the wrong set of numbers, and very confidently output negative 54 million. Yeah, when the ground truth answer was actually positive 187 million.
That is a catastrophic error for a financial task. And an agent restricted to skill-only evolution would try to fix this with that bloated prompting we talked about earlier, right? It would add a rule to its workflow saying, if you suspect the document has a merged header, manually subtract 1 from your row count before calling the extraction tool.
Right, which is an incredibly fragile workaround. It'll break on the very next document.
Right. So how does SkillSmith handle it? Here's where it gets really interesting.
SkillSmith bypasses that fragility entirely by generating an atomic bundle. It tackled the root cause. So first, it executed a wrap operation on the executable tool itself. It wrapped the existing table extractor in a new Python pre-processing layer that resolved merged headers automatically.
Oh, wow. So it allowed the tool to search by specific header string names instead of just dumb integer coordinates?
Exactly. It structurally fixed the hammer.
But the problem is, it still has all these existing workflows that are programmed to send integer coordinates to that tool. If it changes the tool, doesn't it break the old skills?
And that is where the bundle executes. In the exact same synchronized transaction, SkillSmith used the edit operation to update all 3 distinct skills that relied on that table extractor. It stripped out their integer references, replaced them with the new header string parameters, and this is the crazy part, it even added a verification step for the financial units.
That's incredible. It fixed the core logic and instantly retrained every workflow on how to use the upgraded capability, all in one move. So one fix cascaded down and resolved an entire class of errors across multiple tasks.
It creates a permanent structural upgrade to the agent's environment rather than just a temporary prompt injection.
But taking a step back, optimizing a single tool and its corresponding workflow is only part of the battle, right? Because an advanced agent isn't operating in a vacuum, it's juggling dozens of different skills simultaneously to execute a real-world task.
Exactly. The interactions matter just as much.
It's like introducing a bunch of new alpha predators into a tank. Just because a shark is a great hunter on its own doesn't mean the whole tank benefits if it just eats all the other useful fish. The ecosystem matters.
And most evolutionary frameworks completely ignore the ecosystem. They evaluate the utility of a new skill in total isolation. They test it, they verify it works, and they just throw it into the library. But in reality, large language models retrieve and activate multiple skills simultaneously based on semantic similarity.
And so they trip over each other.
Constantly, which is why the researchers literally turned to environmental biology to solve this.
No.
They introduced what they call ecological utility dynamics. They actually adapted the Lotka-Volterra equation.
Like predator-prey biology.
Yes. Traditionally, Lotka-Volterra equations are used in biological mathematics to model predator-prey dynamics, or mutualism, how different species influence each other's population growth.
Okay.
SkillSmith uses this math to dynamically maintain a continuous interaction matrix of all its skills.
So it's actively tracking coactivation. It observes what happens when skill A and skill B are pulled into the same workflow.
Exactly. The matrix calculates a coefficient. If two skills complement each other, say their combined success rate is higher than their isolated success rates, they receive a positive interaction score. But if they step on each other's toes and drag the overall task success down, they get a negative score.
And there is a fascinating breakdown of this failing on the Open Web Reasoning benchmark, SEAL-QA. The agent was tasked with determining what the European Central Bank did with interest rates at its June 2024 meeting, and specifically by how many basis points.
Right. And to solve this, the agent pulled two distinct skills from its library. So skill A was essentially a search breadth protocol. Its core function was to cast a massive net, issue multiple query variations, scrape tons of web pages, and maximize the sheer volume of gathered information.
The ultimate data gatherer.
Yeah. And then skill B was a source authority protocol. Its mandate was to act as a strict filter. So it would aggressively discard any information that did not originate from a pre-approved, highly authoritative domain.
Like the actual central bank's official website.
Right. Now, in theory, gathering broadly and filtering strictly sounds like a solid pipeline.
All right, cast a wide net, keep the best fish.
But in practice, they were fundamentally at odds. Skill A functioned perfectly. It retrieved 23 candidate pages, and several of those actually contained the exact correct answer regarding the rate cut.
But then Skill B activated and the whole pipeline collapsed.
Total collapse. Skill B's aggressive filtering discarded 20 of those pages simply because they were financial news aggregators or economics blogs. It stripped the context down to just 3 approved pages. And unfortunately, none of those specific 3 pages happened to mention the June rate cut explicitly.
Wow. So the agent was left completely blind, and it panicked and hallucinated a 50 basis point cut, completely missing the actual 25 basis point reality.
Exactly. The skills were highly effective in isolation, but totally toxic when co-activated. Skill A's broad retrieval was instantly neutralized by Skill B's aggressive deletion.
But SkillSmith caught this, right? The interaction matrix detected this conflict.
It did. Over several co-activations, the Lotka-Volterra math calculated a strong negative interaction score. It was negative 0.31 between the search breadth and source authority skills.
Okay, so it sees the negative score. What does it do?
Once the ecosystem model flagged that negative coefficient, SkillSmith proposed a compose operation. It explicitly merged the two competing protocols into a single, unified, two-phase skill named search and verify.
So it engineered the conflict into a complementary workflow. Phase 1 executes the broad search, pulling everything in and extracting the claims without immediately discarding the domains.
Right.
Then Phase 2, instead of blindly deleting the unapproved pages, specifically searches the authoritative domains to verify the claims extracted in Phase 1.
Exactly. So it utilized the news blogs to find the claim of a 25 basis point cut, and then targeted the ECB press release just to confirm it, outputting the correct answer.
That is so elegant. So we've established how the system fixes code without breaking legacy dependencies, and how it balances the ecosystem so skills don't cannibalize each other. But evolution is a time-intensive process. A major bottleneck with LLM agents is their lack of statefulness across long horizons.
Hmm.
I mean, they are incredibly prone to amnesia.
Oh, massively. And the framework addresses this through its final pillar, which is anti-pattern memory. It basically operates as a highly searchable, explicit graveyard of the AI's past failures.
A graveyard of failures.
Yeah. When a proposed modification to a skill or tool fails during the validation phase, that computational effort isn't just discarded. The system meticulously logs the failure signature, the causal attribution detailing exactly why the code crashed, and the remedy.
Which prevents what the literature calls amnesic regression. And the wild clawbench simulation demonstrates this perfectly with a complex task involving pushing code to a Git repository.
Right, the git push failure.
So the agent was trying to execute an HTTPS push, but it failed due to an authentication timeout.
And the baseline AI, operating without an anti-pattern memory, analyzed the timeout and proposed creating a brand new skill for an SSH key fallback. However, the code it drafted for this new skill hard-coded a write path to a specific temporary directory.
But an existing clone-to-directory skill was already utilizing that exact folder. It's a classic path collision. Both workflows are trying to write to the same temporal folder simultaneously.
Exactly. The execution crashed instantly and the proposal was rightfully rejected. But because the baseline AI lacked long-term state, it suffered amnesic regression. Fast forward to day 5 of the simulation, the agent encounters the exact same HTTPS authentication timeout in a completely different repository.
Let me guess, it completely forgets the crash from 3 days prior.
It forgets entirely, and it proposes the exact same flawed SSH key fallback skill.
And it crashes again.
Crashes again. And then on day 6, it repeats the entire process. It wastes massive amounts of compute and 2 entire evolutionary rounds, repeatedly rediscovering a known architectural flaw.
Right. But if the agent is properly utilizing an anti-pattern memory, it should theoretically see that directory collision coming a mile away and flag the proposal before it wastes time testing the code.
And that is exactly how SkillSmith operates. When faced with the same auth timeout on day 5, the system's internal reflector drafted the standalone fallback skill. But before moving to the validation phase, it queried the anti-pattern memory. The semantic search returned a 91% similarity match to the failure logged back on day 2.
So it retrieved the causal attribution path collision with clone-to-directory.
And the framework immediately vetoed the proposal. It blocked the code from even reaching the testing environment and redirected the agent. So instead of drafting a standalone skill, the agent simply appended a fallback branch inside the existing GitOps tool.
Wow.
Yeah, it completely bypassed the directory collision and successfully deployed the fix in a single evolutionary round.
But wait, I have a practical question here. You look at all these mechanisms compiling typed operations, updating tools and skills simultaneously in atomic bundles, running Lotka-Volterra mathematics on a continuous interaction matrix, maintaining and querying a massive vectorized failure log. The overhead must be staggering.
It sounds incredibly heavy.
Right. All this continuous integration and unit testing sounds incredibly compute-intensive and expensive compared to just, letting an LLM generate a new prompt. Doesn't this require way more compute power and money?
You would absolutely assume the computational cost would skyrocket. But the empirical data reveals the exact opposite. Now, it is true that each individual evolutionary iteration in SkillSmith carries about a 20% compute overhead.
A 20% tax on every step.
Right, because of the rigorous tool testing and matrix calculations. However, because the system is addressing the structural root causes of failures rather than piling on brittle workarounds, and because it actively prevents amnesic regression, it converges on the optimal solution significantly faster.
Oh, I see.
Yeah, SkillSmith reaches task completion in an average of 13 iterations, compared to 18 iterations for the baseline model.
It's taking a heavier step, but it's taking far fewer of them to reach the finish line.
Exactly. When they ran the final token economics using the Qwen 3.5 122 billion parameter model, SkillSmith ultimately consumed 13% fewer total tokens.
Wait, fewer total tokens?
Yes. It required 16 million tokens to complete the benchmark suite, whereas the baseline burned through 18.4 million tokens just spinning its wheels. And SkillSmith achieved that efficiency while simultaneously boosting the overall task accuracy by nearly 7%.
So it is genuinely cheaper and more accurate because it refuses to waste compute banging a broken hammer over and over again.
Precisely.
And I imagine as you scale up the intelligence of the core model, the ability to utilize this framework only gets sharper.
The scaling laws here are phenomenal. When the researchers tested the framework on the massive Quen 3.5 397 billion parameter model, SkillSmith achieved an astonishing 80.1% accuracy on the Office QA benchmark. That represents an 18.3% leap over the baseline architecture. The smarter the core neural network is, the more adept it becomes at leveraging this external ecosystem to engineer its own capabilities. We are genuinely witnessing a profound transition from static, pre-programmed utility to dynamic, continuous self-evolution.
So what does this all mean? We've moved from AI agents that just helplessly rewrite their own prompts around broken tools to this elegant, evolving ecosystem where an AI can safely edit its own code, balance its skills like a biological habitat, and explicitly remember its past mistakes.
And it leaves you with an incredibly provocative concept to ponder.
I love those.
Right. If autonomous systems are learning not just what tasks to execute, but how to permanently build, refine, and balance the very software required to execute it, and meticulously documenting every architectural failure along the way, we are approaching a fascinating intersection. At what point does this external state, this living, evolving library of custom-built skills, optimized tools, and anti-patterns, become more valuable and more capable than the core neural weights themselves?
When does the tool belt outsmart the carpenter?
Exactly.
It's a wild thought to leave on. Thank you to everyone for joining us on this deep dive. Keep questioning the architectures around you. Keep looking for those deeper mechanical connections, and we'll catch you on the next deep dive.